Hello and welcome to the Plus podcast. I'm Marianne Freiberger.
And I'm Rachel Thomas. So, Marianne, how intelligent are you feeling today?
Whoa, well, that's a tough question first thing in the morning. I must admit I'm feeling a bit tired today, so probably not my most intelligent. And what about you? How intelligent are you feeling today, Rachel?
Well, I too am not feeling at my most intelligent today either. But the good news is we can both rest assured that we are more intelligent in some ways than even the most advanced computer. That's because artificial intelligence, which is the intelligence computers could have, is generally divided into two types. There's weak artificial intelligence, where a machine is trained to do a specific task. And this is something we already encounter every day when we, say, talk to your phone or your digital device or click on a recommended product on some online store. The other kind of artificial intelligence, which is called strong artificial intelligence, or some people say true artificial intelligence, is an intelligence that's inherently indistinguishable from human intelligence. And the standard test for this is known as the Turing test, and it was devised in 1950 by Alan Turing, and it's where a robot or a computer can pass this Turing test if it can have a conversation with a human being and the human can't tell whether the computer is human or not. So true artificial intelligence currently only exists in science fiction. But in this podcast, we'll hear from the machine learning pioneer Yoshua Bengio about why he thinks true artificial intelligence will only be possible once machines have something that we have. And that something is called agency. An agency is where we can interact with the world, we can observe what happens, and we can adapt to the consequences of our actions. So Yoshua Bengio will tell us about how agency helps us to learn and what it could mean for computers if we could just give them the same ability to act in the world.
And at the end of this podcast, in honor of the mathematician Ron Graham, who has just passed away, we'll celebrate our very favorite number, Graham's number, by telling you about it in just 1 minute. Yoshua Bengio is a leading expert in machine learning and artificial intelligence, and he received the 2018 Turing Award for his work. Now, we were lucky enough to meet him at the Heidelberg Laureate Forum last year, when he explains that he thinks that in order for machines to have true artificial intelligence, they have to be more like babies. Not for any reasons that make them more attractive or acceptable to humans by being cute and cuddly, but because it is as babies that we start building our internal model of how the world works, by grabbing, pushing and dropping things and generally interacting with the world. Here's what Bengio said in his Turing lecture.
A 2-year-old, for example, understands physics, now not with equations, of course, it's called intuitive physics, and babies learn this not through supervised learning, right, because their parents don't teach them about Newton's equations. They do that just by interacting with their environment and observing how it works. So this is the kind of learning ability that I think we're missing right now in machine learning and that we need to develop.
Now, don't get worried, there isn't a generation of baby robots in the pipeline. Instead, Bengio told us he wants machines to have a baby's ability to build understanding by interacting with the world, something he calls the agent perspective. And they don't need to be physical robots, baby or otherwise, to do this. Machines have many ways of interacting with the world.
I do think that in order to make progress towards machines which understand better the world, which get closer to human level intelligence, we need machines to interact with the world, just like babies, right? Now, that being said, they don't need to interact through a body just like ours. They could use any kind of sensors and any kind of ways to influence the world. Even when a machine just interacts verbally with a person, right? That's a way to interact with the environment. So it doesn't have at all to be actual robots, But I think this interaction aspect is really important.
So, as we heard in a previous podcast, work in artificial intelligence today focuses on something called machine learning. This is where machines learn how to do a specific task themselves rather than being explicitly taught or programmed how to do it by human programmers. So to do this, the machine are given data sets, which are often called training data, to learn this task from. So you can imagine if a machine is trying to learn how to tell a picture of a cat from a picture of a dog, then it's given a set of hundreds of thousands of pictures of cats and dogs, and it has a kind of learning algorithm that helps the machine tweak the parameters of something called a neural network. And a neural network is just a complicated maths function, and these parameters are tweaked until the neural network, when applied to a picture of an animal, can reliably get the correct answer of whether it's looking at a cat or a dog. And you can find out more about machine learning and the maths behind it at plus.maths.org in the article What is Machine Learning? Now, Bengio told us about how he thinks the agent perspective will become an integral part of machine learning.
So the agent perspective is something that is embraced in reinforcement learning, which is a particular branch of machine learning. But in other camps in machine learning, we tend to ignore it. We tend to think of machine learning as being applied to a given fixed data set. So somebody collects data once and for all, and then the machine looks at all the examples and learns to make predictions, for example. So this is already very useful, but in order to build machines which construct an internal understanding, an internal representation of how the world works, I and others believe that they have to interact with the source of data. They have to interact with the environment in which the data comes about. And so that's the agent perspective. The agent perspective means that the learner can do things in the world, can push things around, and this can have consequences. And those learners need to understand the notion of cause and effect.
Now, at last year's Heidelberg Laureate Forum, where we met Bengio, he had himself just had a very real lesson in cause and effect. During the press conference, Bengio had to have his foot propped up on a chair because shortly after his lecture the previous day, he'd unfortunately broken his foot. He used this as a painful but illuminating illustration of the importance of taking into account the agent's perspective in machine learning and the benefits it can bring.
It's important because when there are agents doing things in the world, it changes the nature of the data. It changes what we call the distribution of the data. Yesterday, I had a little accident, and now the signals that come to my body and my brain are very different. I have to learn to walk differently, and my brain can adapt very quickly to these things. So this ability to adapt quickly to changes in the world due to interventions by agents is something that would be very useful in practice. It's not just a theoretical concern.
Our agency gives us an adaptability and flexibility that currently machines can't replicate. Bengio and his colleagues are working on ways to begin to give machines a similar sort of flexibility. A promising direction for building the agent perspective into machine learning is inspired by how our brains work. If you think about it, we'd quickly get overwhelmed if we paid equal attention to all the information that comes our way every day. Instead, we focus our brain's attention on just small sections of the information we receive. So if we were trying to distinguish between a picture of a cat or a dog, we wouldn't be looking at every part of the picture equally. We'd be ignoring the background. We might even be ignoring quite a lot of the animal's body, and we might instead focus on the shape of the face, the shape of the ears, the shape of the head to tell the difference. And similarly, when we're reading a book, we might be reading one word at a time, but actually keeping in mind other information, such as who the main characters are and what the recent events in the book were. So if you think about it, if I had just read the sentence and I realised the dog had eaten all of it, then the meaning of that sentence is really going to be very different depending on what the it in that sentence referred to. If it referred to the dog's dinner or my homework, that has one kind of meaning. But if it refers to, say, the body of a murder victim, you're reading a very different type of story. Now, Bengio and his colleagues have been developing ways of implementing a similar idea into neural networks, with particular success so far in machine translation. This implementation is a way of a machine learning what are the most important things in a sentence or a piece of text to pay attention to, rather than just having a sort of fixed idea of what it should be looking at. So traditionally, a machine learning algorithm might focus on a window of, say, 3 or 4 consecutive words and kind of slide that window along the piece of text in order to predict what word should come next or to produce a translation of the text. But instead, Bengio and his colleagues are building attention mechanisms that might allow the machine to progress through a whole sentence or a whole series of sentences, but keep paying attention to a few key parts that might be necessary to understand the meaning of the text and the text that follows on. Now, these attention mechanisms have had great success already in machine translation, and this ability to focus in this way has already been included in Google Translate since 2016. And Bengio told us that this could even lead to machines being able to attempt far more advanced types of cognitive tasks.
So the beauty of the sort of attention mechanisms that we have put in deep learning is that they can be trained in the same way that we normally train our network. So the standard neural nets are just machines that process big bunches of numbers always in the same way, right? Always the same computation is being applied at each level in those artificial neural networks. But in our brain, we know that there are attention mechanisms. So what does it mean? It means that we can focus the computation on particular elements, and we have a mechanism that can choose on which elements of what is happening in our brain that computation gets focused, and it can be it can make that type of computation more responsive, more adaptive, more dynamic, because depending on the context, it's not always the same parts of your brain that you're applying those computations to. So in a way, it could help open the door to very different types of applications of neural nets. Instead of being limited to processing things like images and sounds, they might be able to start doing things which look more like reasoning, imagination, planning, and so on.
So attention mechanisms and other implementations of the agent perspective might enable machines to finally achieve a more human-like intelligence. And in his most recent work, Bengio has even been exploring how attention mechanisms might be the key to understanding our own consciousness.
I don't think that consciousness is something so mysterious that we'll never be able to understand it, and it would be something that only humans could have. I think there's no reason to believe that we'll not be able to dissect consciousness into computational functions that we can understand and have machines take advantage of those properties. And I've been working in particular on the aspect of consciousness that have to do with attention, which was part of the topic of the presentation.
In his lecture at the Heidelberg Laureate Forum, Bengio talked about his recent paper entitled The Consciousness Prior, and he explained how attention could have a huge impact on the efficiency of machine learning algorithms. And Bengio also talked more philosophically about how attention mechanisms model what we do with our consciousness. Now, we just focus on a few factors that we can control or that provide us with the most relevant information. So if you think about it, our unconscious state could be all the things you could possibly think about, and then our conscious state is the attention mechanisms of what we are thinking about. Attention mechanisms also have really interesting applications for things like accessing memory in a computer. You potentially can access everything at once, so that's like our unconscious state where we're thinking about everything. but use an attention mechanism that is learned via a machine learning algorithm to only access the parts of the computer memory that are relevant, potentially massively speeding up memory access in computations. You can read more about Yoshua Bengio's fascinating research on plus.maths.org in the article called The Age in Perspective. And now we've come to the part of the podcast where we explain some maths in 1 minute. We were very sad to hear that one of our favorite mathematicians, Ron Graham, passed away last month. Ron Graham was an American mathematician, and like many mathematicians, he lived a wild and crazy life. At one point during his studies, he actually ran away to join a circus. And even after he returned to academia, he maintained his position as one of the best jugglers in America. He even had a specially constructed net hung from the roof of his office in Bell Laboratories. The net had a hole in the center, which he drew tight around his waist, so that when he dropped one of the 6 or 7 balls he was juggling, it would obligingly roll back to him. Graham and his colleagues were working on something called Ramsey theory, which was trying to understand how many different ways a particular type of mathematical network could be configured. And it was during this work that he defined a number that is now one of our very, very favorite numbers. Rachel, can you please explain what it is and why we love it so much in just 1 minute?
Well, I'll try in just 1 minute, but as you'll see, that might be a bit tricky. Now, we first learned about Graham's number when we were writing our book Numericon back in 2014, and it immediately became our new favourite number. And one of the reasons that is because it's really, really big. Now, in fact, Graham's number is so big, the universe does not contain enough stuff on which to write its digits. It's literally too big to write. But amazingly, this huge number is finite. And despite it being so bloody huge, we know it is divisible by 3 and it ends in a 7. And we know that because it's explicitly defined in a really special way. As Marianne mentioned, Ron Graham came up with this number when he was working on something called Ramsey theory. We won't go into that now. You can visit plus.maths.org and search for Ramsey theory to find out all the details about that. But one of the things that's often a part of Ramsey theory is people are trying to give upper and lower bounds for, say, the number of dimensions a network has to be in order for it to have certain properties. Now, Ron Graham managed to find such an upper bound for a particular question, but it was a number that, as we said, was so big it was too big to write within our observable universe. And in fact, the number went into the Guinness Book of World Records as the biggest number ever explicitly used in a mathematical proof. Now, you might wonder how Graham was able to explicitly define such a big number, and he did it using this ingenious notation called up arrow notation that extends our common arithmetic operations of addition and multiplication and stuff. If you think about it, multiplication is just repeated addition. 3 times 3 is just 3 plus 3 plus 3. And exponentiation, or raising something to a power, is just repeated multiplication. So 3 to the power of 3 is just 3 times 3 times 3. And if you use this notation, you write exponentiation as a single arrow operation. Then the double arrow operation is just repeated single arrow operation or repeated exponentiation. So 3 double arrow 3 is just 3 to the power of 3 to the power of 3, which is 3 to the power of 27, which is 7,625,597,484,987. So you can see how numbers are quickly getting huge here. The triple arrow operation is just the repeated double arrow operation. So 3 triple arrow 3 gives you a tower of powers of 3 that is 7,625,000,000,000 and so on levels high. And that is pretty bloody big. Now, essentially, Ron Graham defined his number explicitly using this up arrow notation in a cumulative process that creates towers of powers of 3s that quickly spiral beyond the magnitude of any numbers we can imagine. But the thing that we really love about Graham's number is that this unimaginably large number isn't some theoretical thing. It's an exact number, and we know it's a whole number. It's easy to see that as it's essentially just a multiple of 3 because of the way it's defined as a tower of powers of 3. And mathematicians have learned a lot about the processes used to define Graham's number, including that if it's big enough, the rightmost decimal digits will eventually always remain the same, no matter how many more levels you add to your tower of powers. So Graham's number might be too big to write in the observable universe, but we do know that it ends in the number 7. So maths has the power not only to define such unimaginably big numbers, but also to investigate them and understand them too.
Wow, I really do love Graham's number. And if you would like to find more about it, or about up-arrow notation or Ramsey theory, then go to plus.maths.org and search for any of those terms. And that brings us to the end of this Plus podcast. The music in this podcast is from Ollie Freak, and the track is called Line 1. You can find his music at soundcloud.com/OLIFREKE. Thanks for listening, and bye-bye for now.